So just to review some notions, we're talking about circuits. What is the purpose of a circuit? Remember, a circuit, the purpose is as a mechanism of energy transfer using charge. So we're just trying to get energy from one place and bring it to another place where it can be used to do something useful. Remember, those places, quote unquote, are our resistors. So if I've got my circuit here, there's my battery, negative, positive, we'll label that delta VT for the terminal voltage of the battery. And here is my resistor. It doesn't matter where I put it up on the circuit. So there we go. We have electrons that are being forced to flow. And they're going to flow around like this. They're going to pick up energy, drop it off, pick up energy, drop it off. So the big question then becomes, well, how much energy is being delivered to the resistor? And we're going to find out that that's a more interesting question than maybe we first thought. So let's review some other terms as well. First, let's talk about current, right? So current, remember, is not how fast the charges are going. There's too many of them to really speak intelligently about how fast they're going, but it is the number of charges per unit time. Remembering that current is measured in amperes or amps, which is the coulomb per second, right? And the other thing I want to mention is the concept of potential difference. Potential difference is the change in energy per unit charge, or the work done per unit charge, right? So delta V is equal to, or rather the units of delta V are the volts, which is a joule per coulomb. So what I want to introduce here is two different concepts here about potential difference. When the electron goes through the battery, remember, this is like our electrical pump. Each charge has work done on it in order to give it energy. That's a potential difference, right? But here it's a gain in potential because each of the charges is getting extra electrical potential energy. But then what's happening at the resistor? Well, that's where the charge is going to drop off that energy. So here at the resistor, we're going to have a potential drop. So let's just write down those two ideas. Potential gain, and that's happening at the battery, and potential drop, and that's happening at the resistor. And both of these are delta V's, and if we were being conscious with the signs, one of them would be a positive delta V, potential gain, and the other would be a negative delta V, potential drop. We're not going to get into that. We're going to talk about units today. Because remember, our question therefore is, how much energy is this resistor getting? Well, that must mean that we would care about the potential drop at the resistor. Okay, well, notice, remember, that voltage is telling me joules per coulomb. So in order to know how many joules of energy are delivered to the resistor, what I would need to know is how many coulombs of charge are flowing through that point. Because for each coulomb of charge, I get a certain number of joules. Oh, and then current can help me there as well, because that tells me the amount of current I get per second. Well, if we look at these two things together then, notice what happens if I do a coulomb per second times a joule per coulomb. Doing the dimensional analysis, joule per coulomb, excuse me, doing the dimensional analysis there, the coulombs would cancel out and I would get a joule per second. Now that's not an amount of energy, but it's getting us closer, right? A joule per second, a joule per second. What is a joule per second? What is a joule per second? Right, hopefully I have made this joke often enough. I have said watt is a joule per second. I was not asking a question. I was making a terrible dad joke, right? There it is. So what must this be? This must be power measured in watts. So what's power in the electrical sense? It's a coulomb per second, which is the current, times the joule per coulomb, which is the potential difference. And here we go. We have what's called the electrical power equation. Power is equal to the charge, the rate at which charge flows through it, times the amount of energy delivered per charge. Now, Just because this is true doesn't also mean, folks, that power isn't also equal to work over time. Because if I'm interested here in what's happening at the resistor, right, that work could be doing a lot of things. If that's a motor, that work might be, I don't know, lifting something, so a change in its gravitational potential energy. Or, I don't know, that might be a motor that's in a car engine, and so that's a change in kinetic energy, right? So that concept from before in the course doesn't change just because we've got this in play here. So power is equal to I times delta V. So let's look at that in an example. So let's say I have a simple circuit, and so with a, I don't know, a 6-volt battery, so the potential difference supplied is equal to 6 volts. And let's say in our simple circuit I have a resistor, and just to make the numbers easy, I will make this a 30 ohm resistor. Okay, cool. So then if I were to draw that circuit, I will just draw it in a slightly different way here, just so that we're not getting used to seeing any particular thing. Negative, positive, delta VT, and there's my R, and I could then have my I going around like that. Awesome, so picking up energy, dropping off. Well, how much current do I have? Well, let's look at that. IT here is going to be delta VT over RT, meaning the total resistance that the circuit offers, the current through the battery, the potential difference supplied by the battery, and therefore I get 6 volts, and this is 30 ohms. A volt per ohm is an amp, so 0.2 amps. Now, I could then find power. So power is, so PT therefore would be the power supplied by the battery, or the rate at which the battery is converting electrical or rather chemical energy into electrical energy, and that would be the current through the battery times the voltage supplied by the battery. All right, so that's 0.2 amps, and then this is 6 volts, and that is 3 watts then. So pretty nice and simple calculations there. Now, it should be mentioned here that the rate at which the battery is supplying energy has to be equal to the rate at which the resistor is using that energy or converting that energy, right? That's just a very simple conservation of energy notion there, right? So this PT is equal to, power supplied by the battery, is equal to the rate at which the resistor is converting that energy as well. All right, cool. Now, normally, what we like to think of when we think of power in like 3 watts, you know, your brain probably goes to light bulbs, right? So, for example, as a separate example, you might have a 60-watt light bulb. Here's the problem: 60 watts is it's kind of problematic, because that doesn't tell you really anything about the light bulb, because there's nothing about the light bulb that's inherently 60 watts. What you have to know when we're talking about a light bulb is in the United States, the voltage supplied when you plug into the wall, that's the terminal voltage, is 120 volts. So really what you're doing is you are, there's a certain resistance that that light bulb has. So let's find out what that resistance is. So if I go P is equal to I delta V here, right? So this would be 60 watts. The current I don't know. The delta V is 120 volts. I is equal to 0.5 amps. Now, notice here, I was actually kind of using, if we want to think about it, R as a subscript, because that's the rate at which the resistor is converting that energy. This is the current through the resistor. That is the voltage drop at the resistor. We're going to connect a lot of these things in a video coming up. So there you go. And now I can find out what the resistance of that light bulb is by doing delta V over I, and so that would be 120 volts over 0.5 amps, and that's 240 ohms, okay? Now, if I were to say, well, now I have a 120 watt bulb, what do I know about that bulb? Well, I know that that bulb is brighter because this bulb is converting more energy per unit time. So that still has a delta VT of 120 volts. Therefore, what's happening there? Well, P is equal to I delta V. So I've got 120 watts is equal to I 120 volts. I is equal to 1 amp. So this higher wattage light bulb is actually drawing a larger current. But now when I come over here and I do this calculation, 120 over 1 amp, we can see 120 ohms. And notice here that the brighter light bulb actually has a smaller resistance, which should make sense, because if it's brighter, it's getting either more energy per charge, but that's not true because the voltage is the same because the source is the same. So it must be getting more charges over time. And now we understand why light bulbs are sold by power and not by resistance, even though what is actually determined is the resistance, right? When the resistance is determined by the physical stuff it's made out of. So when a manufacturer is making it, they know what the resistance is. And then because there's an assumption as to what the source voltage is, that's why they can sell it this way. Because I think your average consumer would be really confused if you say like, oh, I'm gonna go get a 120 ohm light bulb, and that's brighter than the 240 ohm light bulb. Usually that's not the way our brains think. We think larger numbers equal bigger things, right? And so that's why American light bulbs and devices are sold based on their wattages rather than by their resistances, even though it's the resistances really that matter. Now, one last thing about this power stuff that I want to go into. That doesn't tell me the amount of energy now, right? So let's say, for example, that 60 watt light bulb, if I want to know how much energy is supplied by that 60 watt light bulb in 1 hour, well, how would I do that? Well, that's when I'm not going to be using P is equal to I delta V. I'm going to be using P is equal to work per unit time. And in this case, what I really care about is the amount of energy that's converted, i.e. the work done at that light bulb. So I'm solving for work here, which takes the place here of the amount of energy supplied, right? Because you can think about amount of energy converted, that's a change in energy because it's a conversion, and that's why it links up with work. So the work is equal to the unit of power times the unit of time. So in this case, 60 watts and then 1 hour, right? Well, wrong, because that doesn't work in this present way. I need to convert this 60 watts, which is a joule per second. Hour is 3,600 seconds. And so there you go. I set myself up to do math that I wasn't ready to do, 21600. Yeah, I think that's it, yeah. So 21,600 joules, and that's just in 1 hour. That's a huge amount of energy for just one light bulb. Remember, we talked about this before. Do you remember the other unit of energy we created when we were dealing with large amounts of energy? Hopefully you do, and hopefully you remember the unit called the kilowatt hour. I can do this same calculation by converting my power to kilowatts, right? So a kilowatt is just 1,000 watts, so divide by 1,000 there to get that. And then I can multiply it by hours, and then I get this as 0.06 kilowatt hours. And those two numbers are identical to one, well, not the numbers, but the amount of energy is identical to one another. Remember when you buy energy from the, I was about to say supermarket, from the power company, you're actually not buying power, you're buying energy from them, and in the unit of kilowatt hour, because we talked about this before, how your parents don't want to be buying billions and trillions of joules, you'd rather buy hundreds of kilowatt hours. So that's the notion here of electrical power. The idea here is threefold. One, power is really easy to calculate for a circuit because it uses current and voltage. Two, that even though we market things in terms of power, it's really about resistances, and so you got to be careful there with your calculations. And three, units really matter when we start talking about power.